Okay, so we're going to go ahead and get started. This is chapter 5. And chapter 5, we're going to be looking over chapter 5, 6, 7, and 8 actually deals with all of this kind of stuff. So we'll be the next 4 weeks, and that'll bring us back to our next test once we get that section done. So the first thing we're going to be looking at is working with digital spatial data and GIS. So this is just kind of setting the foundation for geographic information system, or what we call GIS. We want to see how data is represented in GIS or real world items, and what we'll talk about is what we call the data model. And the data model is really, really important because there's two broad classifications of data models out there. You guys are very used to one type. Most of you are using CAD users of some kind, and that uses what's called a vector data model. But GIS also has another one which is called a raster data model. So we'll see how kind of that works. And that's what they're talking about here, and we call what's called a continuous field. Another name for that would be raster data models. So we'll look at that. And we want to look at what we call non-spatial data, because the one thing about GIS is the strong suit of it is that it can bring non-spatial data and spatial data together, where other types of software don't handle that. They can either handle non-spatial data very effectively or spatial data, but not both together. So that's going to be a big difference. And we'll look at what kind of information that we use in GIS data, and what kinds of GIS are available. So that'll be the last piece that we'll get into today, and talk about some of the softwares and some of those kind of things as we get into this. Okay, so that's kind of where we're headed. All right, so one of the things we've been talking about a lot is about measuring data and gathering data, which you guys are consummate data gatherers because you are surveyors, and that's what your job is. That's what you do. So once we have that, then we need to do something with it. Now, of course, we do a lot of things in the surveying world with it, but mappers might do something else. So we're gonna try to see, okay, how can we utilize this as a different form maybe? And for instance, we may want to analyze where one location lies in relation to another. So you could do this kind of on CAD, but rather crudely. It wouldn't be quite as simple to do that if you were, like, say, had a large map and you were looking at, like, say, where are all the benchmarks within a certain location of me. So that would be a location type analysis. I mean, it could be done, but it probably wouldn't be real easy. And we'll see with perhaps this GIS concept that we can do it a little bit more effectively. Best routes of travel. This would be something that would be really, really hard to do. Let's say just like a straight CAD system. So that's one of the things you can do in GIS. So when we talk about geospatial data, we're looking at examination, manipulation, and analysis of spatial data. And then this is often tied to non-spatial data. So things to think about here is you can do this kind of stuff. You can manipulate and analyze to a certain point in, let's say, a CAD system, okay? With your spatial data that you've gone out and collected, let's say with a data collector, you got your points, you've got all of that. You can do certain things, what we would call spatial analysis to a point, but there's going to be other things that you can't do with that. And then you also have this concept of non-spatial data, which is stuff that doesn't have any locational information associated with it. And you can use a thing like a spreadsheet or a database like Access to do manipulation. Like, say, a spreadsheet, you can have a bunch of information in a spreadsheet and you can do some kind of simple analysis with that, but it's not tied to anything. If we can tie the two together, then we have a lot of power, and that's what this is going to do. GIS is going to tie those two things together for us. So I'll try to point as many examples as we can as we get into this. So GIS then is a powerful tool that's used to accomplish this goal. And like I said, if you just think CAD, a lot of people think, well, GIS is somewhat related to CAD, and it kind of is. But basically, if you have your objects, let's say in a CAD system, arcs, lines, whatever, they're intelligent in and of themselves in terms of like they know coordinates and they know radiuses and those kind of things, but they don't know what's left or right of them or what's connected into them. And that's where we'll start to see GIS is going to bring more of that intelligence into the whole process. And it's going to be able to tie the non-spatial data component into the spatial data component. So geographic information system, or what we call GIS, this is a great definition. If you look it up, this is usually what you see. Computer-based set of hardware and software that's used to capture, analyze, manipulate, and visualize spatial information. So that's probably the most general definition of what GIS is that you'll ever see. And it really is probably more software than hardware, other than the hardware is what you're, you know, the computer that you're running it on. So really, that's what you're looking at. So the information component handled by GIS is what we would call the spatial component, spatial information. So GI stands for geographic information. So, and this is the stuff that has the direct tie to the Earth's surface. So again, it's in some kind of coordinate system. It could be latitude, longitude, or geographic coordinate system. It could be UTM. It could be state plane. And the fact of the matter is GIS doesn't care because it can transform those to any system that you want to work in very readily because it has transformation software built within it. So for instance, examples of what we're talking about in terms of spatial information would be a house X and Y location. So that could be the centroid of the house, not necessarily each corner. So they don't necessarily get as detailed as we do when we look at our civil type software, but at least we have a definite tie to it. Non-spatial data is information that doesn't have any spatial component to it. And another name for non-spatial data is attribute. So we're going to see this term used quite a bit in GIS. They use the term attribute. And it is often linked to spatial data, but when it's collected, it doesn't necessarily have to be linked. So when we're out there collecting information, or GIS people are out there collecting information, they may not have a spatial tie to it yet. So one of the things you're going to have to do in the software is bring these two together. So usually the non-spatial data without a spatial component is going to be kind of worthless, but bringing these two together is very important. And an example of non-spatial data is house value. So once you have a house location, like the centroid of a house location, and let's say a subdivision, and now you can tie to it its house value or its tax base or the zone and those kind of things, all that kind of stuff can be tied to it. Now we can start to do some types of really detailed analysis. So this picture is showing you a picture of typical municipal GIS, and pretty much just about every county in the state now has a GIS of some kind. I'm sure you guys are all aware of that. Probably some of you use it. Cincinnati, Hamilton counties is called CAGES. It was actually one of the early ones. They've been around a long time. This one happens to be in Mahoning County. And he gives you a little sidebar on this. If you get a chance to look at that, he's got a little hands-on application at 5.1 where he has you go in and kind of type in some things and look at it. But like I said, pretty much every county, rural or more less rural, is going to have some type of GIS, and actually some of them are pretty robust. So Butler County has a really good GIS, Claremont County, Warren County, they're all really good. So these guys have been big adopters of this over time. All right, so GIS has a long history, and it's been developed over many, many years. So a lot of people kind of think that this is a newer kind of thing when they hear that term, but GIS goes back to the late 50s, early 60s. So in many ways, it actually predates CAD systems, particularly the PC-based CAD systems, because those didn't come out until the PC computer came about. So everything was being run on big mainframes or something like that at one point. So GIS had a long development. It's computer-based, and cartography mapping, it came out of several different locations. One of the big pushes was this group called the Harvard Labs at Harvard University. So university research started really early, and they developed, I think the Harvard Labs started in the early 60s. And a lot of key players came out of Harvard Labs, people that went on to develop commercial GISs. So I think there was a guy by the name of Scott Morehouse that came from Harvard Labs that was a developer or helped to develop part of the ESRI software. And a guy, I think Roger Tomlinson, I believe, was also a group. So these guys were really early pushers of this thing, developing this. And at the time, you got to remember, at this time frame, you know, computers were in their real infancy. Software development was even really in its infancy. So you didn't have anywhere near the power that you have nowadays. Federal government was an early adopter of this, and the U.S. Census Bureau got into this pretty early in the 70s. They started developing census records and those kind of things that were tied into a GIS, and they still use it quite widely today. In fact, the Census Bureau has a lot of data that's out there that's free that you can use actually in your GIS to build as what they call a base map. So this is a really good source of getting GIS data, at least as a start. So in North America, one of the early groups that developed GIS was the Canadian Geographic Information System, what they called CGIS. And this was a natural resource-based type of thing. And in this, Canada developed, they developed several different layers of data. And again, it was primarily managing things like forestry, wildlife, mining, those kind of issues. So it was more of a natural resource and primarily natural resource extraction. And that was actually early on, GIS was a lot of it. Those were some of the early developers of it. But you can notice that it began in the 60s, early 60s. It was large scale mapping for their natural resources. Canada's a large country. Roger Tomlinson was a key player. In fact, he's considered the father of GIS. I believe he came from the Harvard Labs or was part of that at one time. And by the 70s, it kind of went belly up and went out of business. But it had a pretty long run, and it was, like I said, it was a big developer. They developed a lot of things to be able to use GIS. And so some of the things we still use today, like they were some of the early adopters of scanning, and some of the ways that they handle coordinate systems and all of that kind of stuff came out of these guys. So GIS can be used for just about anything. And I would tell you this, that I think that the fact of the matter is that the GIS probably touches your life a lot more than you think, because retailers use it, you know, real estate people use it, tax people use it, voting, everybody uses it. So it's got a wide range of applications. Okay, come on. So regardless of what application you're using, whether it's agriculture or forestry or any of the things that we're talking about here, regardless of the data has to somehow be represented within the GIS. Okay, so we have to get it from whatever we're mapping into what we're doing in terms of the GIS. So what we have to do is we have to create what's called a data model, okay? And you do this in terms of the computer environment to be able to analyze and manipulate data. So a model is just a simplification of the real world, okay? And so what we're saying is we're gonna assign a certain way of looking at the world in the computer memory, if you will. So we can't like just put reality into the software. Okay, you guys all know that. So like you go out and do a survey, you dump it in Civil 3D or something. That's your data model. Okay, so GIS is kind of working the same way. So the model just represents real world phenomena. And when we talk about this, and you got to think about this, if you look at real world phenomenon, you just think about going out and mapping, just say your neighborhood. There are literally thousands of things you could map, choose to map, or choose to exclude, depending on the level of scale that you were looking at. So one of the things that the data model has to do is decide, well, what is the scale of measurement? Are we going to include everything, or are we just going to include certain things? Because the more you look, the more you're going to see, kind of thing. So obviously there's a point of limitation that you really can't model everything, because you'd have an overload of information. Your computer system just can't handle it. So the data model decides also, besides how you're going to do it, but what you're going to gather, and then there's a scale at which you're going to gather it. So what they do then is you're going to apply a group of rules to simplify or generalize your data. Things like every twist and turn in the, let's say, a river system, you're not going to be able to put all of those in there. So you're going to generalize it. You're going to simplify it. Okay. Those are the kind of things we're going to look at. Or we're not going to locate, let's say, maybe every valve or whatever. We may decide to just have the major manholes, those kind of things. Not that you couldn't, but it just depends on the agency, what they're doing, and how they're going to do it. Okay. So there are two broad classifications of real-world data representation that are used in GISs, and they typically don't use both. Okay. Some of them can handle both types, but usually it's one type or the other. So we have what's called a discrete object view type of data model, and that's the one that's most common. What we do is we conceptualize the world so that we can break it down into a series of simplistic objects. And what we basically say with this type of data model is that I can break down the world into one of three things. And everything out there that I map is going to fall under the category of one of those three things. So there's my generalization and simplification process. Then we also have what's called a continuous field view. And what we're basically saying in this type of view is that, well, things out there don't fall under discrete things. So like manholes are at discrete points. You know, I have a manhole to a manhole to a manhole. So each one of those can be represented with an X and a Y coordinate. But if we look at, let's say, topography can't be just located with one point here and one point there. It's continuous across the landscape. So that would lend itself to what we call a continuous field view. And the best way to think of a continuous field view is to think of surface, even though it's not necessarily a surface what you're mapping. But what we do in this, you're conceptualizing the world in a way that things vary across the Earth's surface and constant what they call fields. So besides topography, you can think of things like temperature. That can be considered as a continuous field view, or pressure, those kind of things. So everything doesn't lend itself to discrete view, and everything doesn't lend itself to continuous field view. But if you have a certain GIS, usually it works either in one format or the other. Very rarely do they do both, okay? And if they do both, they'll do one better than they do the other, okay? So that's kind of an important concept. All right, so let's take a look at the discrete world view or object view. What we're saying is we're going to break the world down into a series of simplistic objects, okay? An object with a fixed location, such as a stop sign, okay? A fixed starting point and a stopping point, such as a street. So it's going to start at an intersection, and it may end at another intersection, or it may start at an intersection and it may end at a cul-de-sac, okay? And the third type of thing would be some kind of defined boundary. So buildings, parking lots, drainage basins, parcels, right-of-ways, these things could be defined as boundaries. So what we have are three different ways of looking at things: a fixed location, a fixed starting and stopping point, and then a definite boundary. And we break these down into this kind of thing, what we call points. And points are referred to as zero-dimensional objects. So a zero-dimensional object is one that is defined by just a simple XY location, or possibly XYZ. Okay? That's considered zero-dimensional. And as we said, things like things that you could model points as would be manholes, catch basins, stop signs, fire hydrants, those kind of things that would be considered probably point objects. Now, here's another thing to think about. Depending on the scale of mapping that is occurring, a house could probably be considered a point object too. Each building, in other words, could be a point object. Because of the scale that we're looking at it, we can't see the actual footprint. Okay, so the scale of measurement, or the scale of what we're doing the mapping at, could determine whether an object is a point always. Okay, so when we have what are called lines, and these are one-dimensional objects, and you create these by having a starting point and an ending point, and also intermediate points. So the best example of that kind of concept, if you think about AutoCAD polyline, where you have the starting vertex, the ending vertex, and all the intermediate vertexes, that's all considered one line essentially. So that's kind of the way GIS is going to represent it. And usually they don't make any distinction between lines and arcs. So that even where you get the term arc map or arc info, they're really saying arc/line. And the third thing would be polygons. And polygons are considered to be two-dimensional objects. And those are going to form areas. So a set of 3 or more lines is going to generate a polygon type of object for you. So again, a building footprint, parking lots, those kind of things that they talked about before. So these are examples of what you would see. These could be representing, like I said, fire hydrants. This could be the road network within a subdivision. And this is the subdivision, and you can see this is your right-of-ways. That could be a polygon, as well as the parcels within it. Those are probably building parcels. And that could be some kind of maybe green space, or it could be a basin of some kind, drainage basin, those kind of things. So all of these could be that. And then these guys can be working over top of each other. But the one thing that's kind of interesting about the way GIS works, the data on this can't really be part of the data on this. So these will have different layers of information, but you can't have line information on a polygon layer, and you can't have point information on a polygon layer. So the layers will be separate based on how they aggregate stuff. Okay, so collectively, these are what we call vector objects. And again, your best concept of this is AutoCAD, because AutoCAD is what you would call a vector database. So it is calculating everything vector-wise. Okay, points, lines, and polygons, then these become your real-world phenomenon model. So we call this the vector data model. Okay, and it's just, again, it's just a way of simplifying what you're dealing with or what you're generating there. So the most commonly used GIS out there uses that vector data model. It's not used across the board, but I would probably tell you this, that almost every municipality that you run across is going to have some kind of software that is more vector-based than the other type. Now, when you get into maybe other scientific applications, where guys are maybe doing more environmental stuff or forestry or those kind of things, they're not going to favor the vector data model. They're going to use another type of data model. And we can, like I said, you can use both of these sometimes together. Some of these softwares can use them both, but they're a little hard to get because they're separate data types, so they don't really blend really easily. But yeah, commonly used is the GIS and the ArcMap. If you use that, that's a vector data model. Some of you might be aware that AutoCAD has a GIS software called ArcMap, or Map. It's AutoCAD Map. And actually, if you're using Civil 3D, Map is actually embedded in that. There is a section of Map. So you really do have a GIS built right into Civil 3D. So a lot of these guys are utilizing this. Okay, so let's go on here. Okay, so that's just your conceptualization. So we're breaking the whole world down into points, lines, and polygons. And just remember, depending on the scale of what you're measuring, that's going to make a difference what becomes a point and what becomes a polygon. Okay, so just keep that focused. Now, usually as a user, you don't really have any control over that. The people that decide that, like say in a municipal GIS, those decisions were made a long time ago. When you're adding data or utilizing data, you just got to keep in mind how that works. Okay, so there we go. Map scale is going to directly or greatly impact how that vector model sees things. Okay, well, how it's used to represent data. So here's a good thing. I've already iterated this, but county level representations at that level, fire hydrants might be equal to points, buildings, polygons, but at a country level representation, basically fire hydrants will disappear. So cities might go to points, buildings will disappear, and you'll be left with states that are polygons. And your roadway networks, those are probably going to be lines. Okay. So this is a good example of what we're looking at. In fact, you're going to see this map in on Thursday, because this is just a data set that we're going to be generating. This right now has 3 levels or layers of information on it. And you have what are called point layers, polygon layers, and line layers. And I think it's pretty easy to see that what we're looking at, the polygons are the state. There's your state of Ohio, Michigan, Indiana. These are selected points. Not every city within the state is represented here. So again, someone made a choice to decide maybe cities that were less than a certain population base just got lost in it. And then the lines, if you look at this, these are probably, looks like they're representing interstate highways. And you may have other road networks on here, but they like AutoCAD with layers, you can choose to turn them off. So we may only be looking at an interstate layer, a major city layer, and then a polygon layer. Okay, so there's there's a large amounts of data that exist in GIS, and of course things have to be constantly updated. Just think about, for instance, a municipal GIS in this county or the county wherever you are. You know, subdivisions are constantly being built. Building lots are being added all the time. So those parcel databases have to be updated constantly. So that's a big part of what the GIS people in those areas do. So to update data, there's a couple different ways to do it, but your author talks about this process of digitizing. And digitizing is probably an older method of generating data, but what it allows you to do is, in the early days, let me preface this by saying, in the early days of GIS, digitizing wasn't one of the major ways they got information in GISs, because they didn't have digital data that was just out there that you could go grab. So you could take a paper map and you could tape it down on a device called a digitizer, which was basically just a big flat tabletop that had wires embedded in an XY pattern, you know, some running horizontal, some running vertical. Then you ran a thing called a stylus across the top of it. And what you would do is you would get to a point where you want to like put a point in, you would click that point, say I'm going to draw a line from the next point to the next point. What it's doing is it's encoding that map from a paper into a digital representation. So we used to have a very large digitizer at one time at the college, and it looked like a very large drafting table is what it looked like. And you could tape your maps down, and you had a stylus that went across it, was called a puck, and you would basically link that in with your software, and you would digitize information in. So your author kind of makes it sound like digitizing is a real common way of doing this, and maybe in the beginning days it was, but I don't think it's as common anymore, because there's better ways to do it. But this allowed you to create points, lines, and polygons by just doing that process. And by tracing or sketching that image, you can now use a mouse, and what they'll do is what's called heads-up digitizing, where you can take and do this on screen. If you've ever taken an image and brought it into AutoCAD, so you can take a PDF file and you can bring it into AutoCAD, and then you can trace across the top of it, draw lines across the top of it. That's basically heads-up digitizing. It's the same process. And if has anybody ever done that process?
Yeah, I do it with some regularity.
It's pretty laborious, isn't it, Ben?
Yeah.
Yeah, luckily most of the time we're just trying to get like utility, like a few lines of utilities.
Right, but it's a big deal, right? I mean, it's a big process. You got to worry about scale and all that.
Right. Yeah,
you got to distort picture.
Make sure the drawing looks overlapped or overlays properly. Yeah.
Yeah, and then, well, the other thing about it is, I mean, if you do that all day long, trust me, that is like one of the most mundane, boring things that you can do, and you may start out really pretty good, and then as the day wears on, you're gonna get tired of doing it.
Pretty soon you're jumping over the points.
Yeah, absolutely.
Contours is what is a real pain.
Oh my gosh, yeah, doing a contour trace is that's horrible. I mean, but it's a process, right? It works. It does work, right? But
absolutely.
but it's just not the favored method. But that's, and you guys are familiar with this process. That's what they call heads-up digitizing. If any of you guys use a real digitizer, the old process digitizer I was talking about, anybody?
I
have
have,
not seen
with,
Not anymore.
Yeah, no, not anymore. They've disappeared. I don't even know if you can buy them anymore.
I don't think so.
Probably not, because heads up has taken its place pretty much. But yeah, that was a big deal at one time.
Yeah.
Yeah. So it's tedious, it's time consuming, it's not super accurate, and it depends on the user. Like I said, you may start out.
That might have been at least more engaging than doing it on the screen.
Yeah, well, could have been. But I'll tell you what, being hunched over that board all day long,
Yeah.
it's pretty intense. And so we've done it both ways. But yeah, the good news is you don't normally have to do this as much anymore. There are actually some programs that you can actually bring in a raster file, and they will actually trace vectors across it for you, and then you just have to do a little cleanup. Those are kind of cool.
I believe AutoCAD has that raster program to do that.
It does. It's called raster design, I believe.
Yeah.
That's true. So I don't know if it traces it for you automatically. Does it, Greg? Do you know?
You know, it's been so long since I've used it. It's been years since I've even used it.
Yeah. Well, there was another program. I forget who made it, but there was another one that actually it would just kind of take off and start tracing lines for you, and then you'd have to do a little bit of a cleanup process on it. But
Yeah, I've used that one as well, which I thought worked better than the AutoCAD one. But
it probably did.
I can't remember which one that was either.
Yeah, I forget. It was a big company. I forget which it was, but might have been MicroStation or somebody that wrote it. But anyway, so these things you can expect lower accuracy results. That's pretty true with this process. So this is showing you a picture out of the book where he's looking at the left side is basically a photogrammetry picture, and what they're doing is they're tracing this as a polygon, and then it's generating a polygon, and after it generates a polygon, that's calculating the centroid of that polygon, and that'll put that into whatever layer you want that to be on, and then you can actually then attach attribute information to it. So it's a tedious process. So objects created in GIS may have explicit coordinate locations, but they also have to have information about how they interact with other objects. Okay, so if you go in, for instance, in this picture we were just looking at, you generate a polygon here and maybe a polygon someplace else and a polygon someplace else. You just have 3 polygons on a layer, but they don't know how they interact with each other, whether they're supposed to touch, those kind of things. So we can enforce relationships or rules about this, and this process is referred to as topology. So you build what's called topology after you've represented your vectors, your objects, your points, your lines, whatever. Then you do this process of topology, and what that does is that allows objects to determine how they're connected to each other. And the 3 major things you talk about with topology is creating what's called adjacency, connectivity, and containment. Okay. So it allows that thing this is what brings in the intelligence, okay? Essentially, like for instance, when you draw a polygon in AutoCAD, and you can have a polygon next to it or across, let's say you have a 4-sided polygon with polygons touching it on each side, such as you would in a subdivision. Those polygons don't know what they're touching. They don't know what's left and right. They know what their geometry is. They know what their area is. They could even tell you their centroid, but they can't tell you what's left or right, or what's, how close something else is. And when you go into GIS and they have this process called topology, you can do that. And like I said, if you have Civil 3D, there's a section, you can get a different menu in there that you can go into their GIS section, and they have one that allows you to build topology out of your objects. So a DLG, a digital line graph, this is a type of vector data that is available to GIS users. This comes originally from the USGS, and what they did was basically took all of their USGS paper maps and they digitized them in some way. I'm not sure how they did it. I don't know if they sat down and did it by paper tracing, but they've converted all of those to these DLGs, And this is distributed free, so users can use this information and bring this into GISs, and it's already built for them. Now, it's at a scale that's not really conducive to doing, real close-up work, but it's not bad. So these are digitized from USGS topographic maps. I'm assuming, does everybody know what a USGS topographic map is? I'm making that assumption.
Yeah.
Yes.
Okay. So they come in
Yeah,
where
you can pull them all up online now too.
Yes, you
Yeah.
can.
It's kind of neat to look at the old paper copies next to each other.
Oh,
online.
the paper ones were awesome. I mean, if we used to have our office. I mean, we had basically every USGS map within, an area around, because we used them so widely, and they're beautiful. They're just like beautiful pictures. But it's probably, I think you can still buy them, I think, but they're really hard to find. Not like they used to be able to. You could probably go into every courthouse and get them at one time, but they don't sell them that way because they got them this way. But they're usually come in different.
Yeah, you can go online and just click through all the historical ones now.
Mm-hmm.
I can't remember exactly where it was. But
Aren't they in CET files or something like that?
Yeah. You can probably find them that way. Those are different. Those are different types of things. They come in what are called different series. They usually have a 7.5 minute series and a 15-minute series. Are you guys familiar with what that's referring to? Anybody?
yeah, the amount of longitude it covered, wasn't it?
It's both latitude and longitude. So
Okay.
it's 7.5 of longitude by 7.5 latitude. Yeah.
And that's miles, isn't it?
No,
It's
that's seconds of
degrees.
arc.
Oh,
Yeah.
that's just seconds.
Or not
Okay.
minutes. I mean, it's minutes. 7.5 minutes.
Okay.
Yes, because it's based on a latitude and longitude, which is an angular type of coordinate system, right?
Gotcha.
Yeah, so that's what that is. And the 7.5 minute was a 1 to 2,000 scale factor, or 1 to 20,000, excuse me. And the other one I think is a 1 to 50,000 scale factor. So they're not real high level. Okay, a lot of the stuff is at the scale. You can't see a lot of things. In fact, a lot of buildings they don't even show, and even some that have bigger footprints they'll just put a square. So, but these are free. I mean, you can go out to these groups. These are vector data sets that have been generated, and you can get this information. It's broken down into layers, and you can utilize it in a GIS. So they have things like transportation, which would be street, highways, railroad type stuff. They have hydrographic features, which would be things like your lakes, rivers, and streams. Now, of course, streams are at a certain point, streams are going to disappear because they're not going to be able to be shown at the scale. And usually, they only put what's called a perennial stream, which means you have to have water in it like maybe 7 or 8 months out of the year before they'll actually even show it on the map. And then you have boundary features and things like state, county, city. It's very interesting since you guys that are surveyors, USPLSS system is on there. The U.S. Public Land Survey system is on there. If you're in an area that has them, and if you're in an area that doesn't, like say across the river in Kentucky, that's not a USPLS state, so it won't show those kind of things. And of course, it's freely distributed by USGS. So you can go out to their webpage, you can grab whatever map you want and download the data sets, and you can then pop that into a GIS. So it's pretty cool, actually. Has anybody ever done that?
I looked at them in my geology class in the spring.
But you've never done any download of the data?
We didn't download anything,
Yeah.
no. It was just doing you could do analysis with their simple tools online.
Yeah. Which is basically a kind of a little miniature GIS is what they actually are using here.
Yeah.
Yeah, absolutely. Cool. All right. So this is an example of a DLG. This happens to be the name of the map. Maps you guys are familiar with. They always name them with some generalized feature. This happens to be what's called the Youngstown Quad. So these are referred to as quadrangles. And so what we'd be looking at is this would be 7.5 minutes of longitude from here to here, plus 7.5 of latitude this way. And you can see there's your roads, your rails, and your hydro, and your boundaries. So this contains a lot of information in that. I don't think it comes with, there's not going to be much attribute with information with this. So it probably, and I don't think there's any actually. So all it is just vectors. but you wouldn't know what the name of this road is, kind of thing. So that would have to be brought in as another subset. So here's another one that your author talks about that's also free, the National Hydrography Data Set. And this is also distributed by the USGS. So this is dealing with water boundary type stuff primarily. And so it's got layers associated with various types of water boundaries. So you have line objects, you're gonna have such things as rivers and streams, polygon objects, which would be things like ponds and lakes. And then this one will have attributes attached to it. So the difference in that other one, you don't get any attribute data. So it's basically just a bunch of vectors. So if you need to tie that in with something, you have to actually build the attribute tables. Here you'll actually get attribute tables. And we'll talk a little bit more about attribute tables here in a bit, but you're going to see attribute tables on Thursday because we're going to be working with the GIS software, so we'll see that kind of stuff. So this is also freely downloaded from the web for GIS use. So this is an example of Virginia Beach, Virginia, of a national NHD data set. And you can see some of the different stuff that it has. And this would be considered for line data right here, okay? And this would be considered polygon data, okay? So you can notice the difference. You can see over here on the map, that's line data. But when you get things like, oh, well, this swamp and coastal marsh area, this is built in as a polyline, okay? So these are, when you see this is usually indicating this is polyline type data, and this is line data, and there is no point data on this apparently. So that's all you were looking at, yeah. Okay, so not everything that we deal with in the real world can be considered a fixed boundary or such as a simple object. So we have to handle that differently. So things like temperature. I mean, temperature, if you think about it, no matter if you were in a room or out in the woods or something, every place that you would be could potentially have a different temperature value. And if you sampled it infinitely, you would basically generate a surface. So we would think of that as a surface. Same thing with elevation. We understand that implicitly. Barometric pressure. So these are examples of things that don't have a fixed boundary or a fixed object point. Okay. So these things will vary across the earth, and these are best modeled in GIS not as vector type data, but as a different type of thing. We can think of them as a surface, and you can think of it made up of a near infinite number of points, but we don't actually use points. We do it a little bit different, as you'll see here. And this is what we would call a continuous field view of representation. The continuous field view is just conceptualizing the world so that you have those things that vary across the Earth's surface as what we call constant fields. And what this allows you to do on this type of GIS is everywhere you put your location, you're getting a value, okay? With a vector GIS, everywhere you put your cursor, you're not necessarily getting a value, because if I'm not hitting either a line or an endpoint or something, I'm not getting a value. Where with this, everything that you're representing there is got a value associated with it. So the whole map has values associated with it. And this is what we call raster data model, or we use what's called the raster data model to generalize this data. So this is a bit different because most of you probably not use this too much, although you've seen it before, certainly. Actually, your computer screen uses a raster. They call them pixels. So it's just a group of area that generates the light that you're seeing. And the way we do this is we take that spatial data and we use a series of equally spaced grid squares. So one of the easiest ways or best ways to think about this is you think about taking take a big sheet and you lay a grid out on that sheet. So you break it up, let's say, into 1 foot grid, square, and you lay that out on the ground. So each one of those squares, then you can get a value of elevation within that square. Now, certainly the four corners of that square would probably have a different elevation value, but what you do to simplify it, you're either going to take the average of the four elevation points on the square, or you're just going to sample the center. But what happens is the square itself only has one value. Okay, so you only get one value out of this. So the grid square, it's just a square unit typically that represents your real world thing that you're sampling. The size of the grid square will make a difference, okay? But this allows you to represent an entire section of landscape. So again, keep in mind that you're getting a value everywhere that you're sampling essentially. So the grid size might be 10 square feet. So 10 feet by 10, 10 by 10, or 30 by 30, or 1 kilometer. So notice as we're going from 10 square feet to 30 meters squared to 1 kilometer, those squares are getting increasingly bigger. So as we're going from a smaller grid square to a larger grid square, we're generalizing a whole lot more, okay? We got better data in this because these cells are smaller. So this is referred to as resolution. So the smaller the square, the better the information. And you talk about cameras, we talk about pixels, megapixels, that kind of stuff. Photographers, you know, the better your pictures, you're going to get better pictures with more megapixels, those kind of things. So it kind of works the same way with GIS, but then again, you have a point of diminishing returns. You can't have an infinitely small grid square, so they are going to be limited. Okay, so each square within the raster has to have the same resolution. So in other words, you can't have some that are 10 square feet and next to it some that are 20 and then 20 and 10. So if it's a 20-meter resolution, then it's going to be 20 across the board. You can't mix them. Each square that you sample contains a single value. So again, if you go back to my example we were just talking about, if you sampled the four corners and elevation of a grid square laying on the ground, they're not all going to be the same. So there's rules that are going to be enforced. We're either going to take the average of those four, or we're just going to sample the center. But that we're going to call that whole grid square 800, whether the corners are bad or not. Okay, that's how that works. So it's a simplification, generalization. So it's not perfect. Okay. Each raster map that you have contains what we call one theme. So for instance, one theme could be elevation. So it could be elevation or soils, but not both. So if you want to express both into your GIS, you're going to have one raster, or you could think of it as one layer of elevation data and another layer of soils data. Now you can overlay those guys on top of each other and do analysis from grid square to grid square, but you cannot have elevation and soils on the same raster. So you are limited.
Jim, did I miss something? But what exactly is a soils?
Soils
Is that just a form of data?
Well, it would be like the soil type. Have you ever heard of a soil?
Okay.
Okay, yeah. So what I'm talking about is like, you know, you got clays or silty clays,
Okay.
or, right? You know, or whatever.
I just wanted to make sure I
No,
understand.
that's cool.
how
No, you
it's
didn't.
being-
No, that's good. Good point. Good point. I just assumed everybody knew what I was talking about. That's good. Yeah. So you have those kind of breakdowns as well, right? So I mean, there's potential all kinds of different things that can be mapped, right? So this is a generalized schematic of what we would look at in terms of what we would call a raster. And what they're showing is kind of interesting is that these guys right here, these would be the smallest unit right here that you're looking at. Okay, so if we say we had a 20-meter resolution, that would mean it's 20 meters by 20 meters, or 10 feet by 10 feet. Okay, so the total number, this would be the number of columns that you have. Okay, so this would column 1, column 2, column 3, like this. And this would be row 1, row 2, row 3, row 4, row 5. Usually, they start at this one, and they go across this way for the column numbering, and they go this way for the row numbering. Okay, and that kind of has to do with the way satellites gather data, because a satellite, as it flies over in this direction, and it has a sensor that sweeps in this direction. So as it's going this way, it's gathering the data row by row by row by row, like that. Okay. Now, some people would call this column 1, row 1, and some softwares use 0 and 0. So this might be 0, 1, 2, 3, or it could be 1, 2, 3, 4. So that just depends on, I think it depends a lot on the software system, okay? You can also notice that you have this coordinate system right here, which could be X and Y. So you could have an origin over here. So theoretically, I could put my cursor here and I can get an X and Y location anywhere within that grid square. So I could talk about the location of this being at row, what, 1, 2, 3, 4, 5. So that could be a column 1, row 5, or it could be some X and Y value. Or if you were using latitude and longitude, longitude would be coming this way if we're in North America, and this way latitude would be coming from the equator up. So you could really get 3 different coordinate systems out of this, depending on what your data format's in. Okay, does everybody get the idea?
Yes.
If we talk about
Yep.
If we talk about a grid square here, you know, just as a column and row, then you're really talking about that whole area right there. And keep in mind, this whole area just has one value. If this is value 800 for the elevation, the one next to it might be 802. This one might be 805, okay? But you're not gonna find like between 800 and 800, you're not gonna have 801 anywhere in here, okay? It's just, each one of these have discrete values with them, okay? So that's kind of different too as this process. Okay, so one of the things your author also talks about here is what's called the National Land Data Cover, the NLCD. This is another group that has regional information for raster data in the U.S. that you can get information from, and this is based on a 30-meter resolution. So it's 30 meter by 30 meter. And what this is showing you is land cover types. So they've got this for the entire United States, and you can, again, this is also freely shared data from the federal government. So each cell, each 30 by 30 meter resolution cell corresponds to a specific cover type. They've broken it down into many different kinds. So they have like open water, they have developed or high intensity, they have deciduous forest, coniferous forest, all different things. And what this does is gives you a broad scale classification. You can do it at regional, state, or national scale. And these have been available, 1992 is when they started. And then they update it periodically, 2001, 2006. I think your book talks about there being a 2011. They probably have a new update to it. He has a web page. I haven't checked it out. You guys might want to check it out. It's kind of neat. But this is showing you actually a 2001 data set, and this happens to be from Columbiana County in Ohio. So this is an Ohio County data set. And what you're looking at here, it's kind of hard to see because you can't zoom up on this, but what you're noticing is clearly these are rasters. So if you looked up, if you zoomed up into this, you would see a bunch of grid squares. You can't really see it at this level. But you do notice, like for instance, open water, there's lakes here. This would be down where the Ohio River is, I believe, that point. And you can notice there's deciduous forest, evergreen forest mix. So you can see there's a lot of differences in here. A good portion of this county looks like it's in cultivated crops, pasture, grasslands. So you can see a large chunk of there. But when we get over here, which is probably closer to a little bit more hilly areas, we're seeing that more tree cover. And of course, in the developed areas, it really sticks out. These would be pretty good sized towns. I think that might be Youngstown, actually. I'm not 100% sure on that. Okay, so regardless of what you're mapping, you could have a layer of polygons that represent house footprints, another layer that represents highways or driveways, whatever. Your GIS contains information about the spatial properties, but it's also going to need other types of data, okay? So if you have, let's say, a subdivision where you've developed footprints of each structure within that subdivision, and maybe one that represents driveways, that's all good and well. You've got good spatial data, you've got good latitude, longitude, or whatever. system you're in, but you also need other things. And so that's where we get this non-spatial component, okay? So we might want to know what is the tax assessed value of each house within that subdivision? What is the address of each of those? What's the owner's name? Okay, on and on. All this information is just strictly speaking, it could be tabulated in an Excel spreadsheet, okay? But it has no tie to the earth. So what we can do is if we can take this information and somehow tie it together with the polygons or the lines or whatever, then we have a lot of power. So this is your spatial component. This is your non-spatial component. And that non-spatial component is what's typically referred to as an attribute. Okay. You'll hear the term attribute used a whole lot more in GIS than you will non-spatial, but they're kind of interchangeable. So attributes, they can take one of four forms, and what they call, this is referred to as scale of measurement. Okay, scale of measurement, we call it nominal data, or ordinal data, or interval data, or ratio data. So nominal data, just think name. So that's name only, essentially. Ordinal refers to order. Interval is the difference between two sets. And ratio is where you have a zero, okay, location. So nominal data, it's a type of data, it's just a unique identifier of some kind, but that's about all it is. So for instance, a list of social security numbers or a list of telephone numbers, that's just considered nominal data, okay? And you can't do things with it. I'll show you here in a minute, but if you take social security numbers, you can identify things with that, you know, the person that it's attached to essentially, or telephone number. So it's just an identification. Your name, you know, your name, Jim, Bill, or whatever, that is just, that's also an example of nominal data. Mathematical operations would not be valid. So multiplying two social security numbers together doesn't give you anything. It's not going to yield your cousin's social security number. Okay, so any kind of mathematical operation is invalid on nominal data. All right. Subtracting phone numbers is meaningless. Any of that kind of stuff. Right. So ordinal data is a type of data that just merely gives you a ranking scheme or an order in which something occurred. Okay. Now, it doesn't tell you the interval at which it occurred, just the order at which it occurred, okay? So here's an example. If you had winners in a race, you had the first place, the second place, and the third place, okay? The first place and the second place, those guys could have been maybe 1 second apart, okay? And the second place and the third place, they could have been 5 minutes apart, but we don't know that. With this type of data, all we know is that this guy came in first, this guy came in second, and this guy came in third. So interval is not established with ordinal data, just the order in which it occurred. So you can think of it as a ranking, okay? Just strictly as a ranking only, okay? Again, mathematical operations are not going to be valid. Subtracting 1 from 2 doesn't give me anything, okay? Or 3 from 1. I don't get anything based on that, okay? And first place is not twice as fast as second. Doesn't say that at all, right? So then we come to what's called interval data. And this is a more numerical type of data in which the difference between numbers is significant, but there is no fixed arbitrary 0 point. So you can go above or below 0. So 0 has no specific meaning. It's just another number within the number line. So subtraction in this type of thing makes sense, but multiplication and division does not when you have interval data. So a good example is the Celsius scale is an interval data scale. So 30 degrees Celsius is only 15 degrees warmer than 15, but not twice as warm as 15, okay? So it's just the difference makes sense, subtraction makes sense, but division doesn't. So the highest order of data is what they call ratio. So this is a type of numerical data where the difference between numbers is significant and it has a fixed non-arbitrary 0 point. Okay, so in this system, mathematically, subtraction makes sense, so does multiplication and division. So an example, 0 has a specific meaning, So in other words, data cannot be less than 0. So we can talk about where multiplication and division makes sense with this data. So a person that weighs 100 pounds is twice as heavy as a person that weighs 50 in this system, okay? So this is the highest order probably of attribute data that you would see. And GIS is if you try to take, like say, ratio data and multiply it with ordinal data, it knows, so it's not going to let you do that kind of stuff. So it's kind of intuitive or intelligent in terms, because it knows what type of data that you have. Okay, so each layer in a GIS will have an attribute table that's associated with it that stores information about the features on that layer. So for instance, what we're saying is if you have polygons, okay, as a layer, and let's say those polygons are parcels, there is an attribute table that's associated with those parcels that can then maybe tell you owner's name, area, zoning, all of that kind of stuff. As long as somebody has built those polygons and then built the topology and built all this. And we're going to look at data that's going to have this. So when you fire it up, you open it up, it'll have an attribute table with it. So this thing called an attribute table, I kind of equate it looks a lot like an Excel spreadsheet. In fact, it's very similar. It's not a spreadsheet, but it's very similar. And it's in a spreadsheet style where you get columns and rows of information. And then you have those attributes that are associated with objects, or you can think that they're linked to those objects. That's a critical component of this. And we don't use the term columns and rows when we talk about attribute tables. Records are what is preferred for a row. And rows of data, each row is establishing or linked to one unique object, okay? So each row is associated with one unique object. So if you have parcel 1, 2, 3, 4, 5, then you're going to have rows 1, 2, 3, 4, 5, or records 1, 2, 3, 4, 5. So record 5 might be associated with parcel 5 kind of thing, but you can't have it with 1, 5, and 6 simultaneously. Fields are what they refer to as columns, and those are the things that run down vertically, and these are your attribute values themselves. Okay, and you can have multiple fields of data across your table. In fact, you can have hundreds of fields literally, and hundreds of records actually. So it just depends on the size of your GIS. So this is a really good example showing you this. So notice these are object features right here. And what would you say we have? Polygon, point, or line data here? What do you think we're looking at?
Isn't that polygon?
It sure is. It's polygon. Look, and if you look over here, there's that symbol. That symbol is typically telling you your polygon. So if you had a line data, it'll show you a line. If you had a point, it'll show you a little point symbol. So this is polygon data, and this is the attribute table associated with this. So when you pull this up, this layer right here, this is what you're going to see on your map. And then you can click on this and open up the attribute table. And what you're looking at is these guys running this way across this way. Those are your records, and these are your fields. And these guys right here, that's referred to as your attribute name right there. So you notice state name is the attribute name, and down in this, these are the attribute values. Okay. So notice as I go down the column here, I'm going into different polygons, right? But everything in here has to be of this type of data that would be state name. You wouldn't find area in here, okay? So you have region, you have state abbreviation, you have population based on a certain date. And this table could scroll way over because it could be hundreds of fields worth of data. If this truly is just states of the US, you're going to basically just have 50 records, okay? So the records can be smaller depending on what the data is representing on the map. All right, does that make sense?
Yes.
So very much like an Excel spreadsheet would look. In fact, you can even do things like take and you could sum this column. So you can do a lot of the similar types of things that you can do with Excel. In fact, I think you can actually export these out as a CVS format, so you can open those up in Excel, and vice versa. I think you can actually bring Excel data into these things and link them. Actually, we're going to talk about linking tables because that's a pretty cool thing to do. Okay, so this is This is an important thing. You're going to see this. And again, we tend to call these columns, but GIS people tend to call them fields, or database people. And these are, we a lot of times call these rows, but this is tend to be referred to records. Okay, that's their preferred method or terms. Okay, so consider an attribute table for vector data. Let's say a housing example where you have 5 records and each represents a house polygon. And then you have fields such as owner, which would be nominal data, appraised value, which is ratio. That can be created or added. And in a way, you can take non-spatial data that is associated with spatial data and you can link them. So if you have raster data, usually they don't have attribute tables for raster data. Typically, just the data itself is handled within the raster. But rather than having a separate record for each cell, the record is the created value of the cell, essentially. So county land use raster contains thousands of cells, but you just use 7 unique values within it. So typically with raster data, you have the data that is the raster, and the values in the cells, those are actually all the data. So you don't have a separate table associated with raster data. It's a little different. And what this is saying is you may have a county land use type of raster that may contain thousands of cells, maybe hundreds of thousands of cells, but they're only breaking it down into 7 unique values. So land use might be agricultural, and then it might be industrial and residential. So you're going to assign a number for each of those, and usually they color code that. Like we were looking at that other raster of the land use type. Like it's usually color coded. Okay, so you create 7 records, 1 for each value, 1 for water, 2 for deciduous forest, etc. And then your attribute, just the sum of those cells containing value. What you can do is some pretty cool things, like you can go in and you can have your raster calculate the number of cells that are valued water, and it can rapidly tell you how many cells. Like for instance, you can have, like say I got 8,503 cells. And further then, if your raster is so many units by so many units, you can determine the area of that really easily. Because if your area, let's say, just theoretically, let's just say each cell is 1 acre big. 1 acre times the number of cells will tell you how many acres you have. So it can calculate things like area very rapidly. Raster is very quick at doing that kind of stuff. Okay, so big distinction then is that between the raster and the vector model, vector is going to have the vector objects, and associated to that are going to be attribute tables. And basically with raster, the raster itself has the data, so there is no attribute table. Okay, we're not going to do a bunch with raster because the software we're going to be using is pretty much vector based, but I'm going to do some things with you because I want you to appreciate it and understand it. And raster is pretty easy to do by hand using grid squares and things. So I'm gonna give you some examples of that. We'll do a couple of homework problems based on that. So one function, if you are dealing with data that you have, let's say you have some data on a map. So we're talking vector now. You have data on a map that has an attribute table associated, but you have another attribute table that is not associated with any data. But if it has values in common, let's say you've got states and you've got another table that has states, you can link these 2 tables. And what that allows you to do is join them such that the data that didn't have any spatial component to it is now linked to the other one. So now it's linked into the spatial component. And what you do with this is use what's called a join function. It's actually a really cool process. So this allows you to link 2 tables or more together, one that may not have a spatial component to it and one that does, and they have to have a commonality. So your non-spatial data can be connected to one that is linked with spatial data. And in order to do this, the tables have to have a common field. Okay, so remember the field is the vertical lines. So for instance, state in one and state in the other. And when you have the 2 fields that are in common, this is called a key, okay? So basically it's like the key in one fits in the lock in the other kind of thing, okay? So the values, they have to be the same in both tables. So they would have to be the same. What we're saying is they have to be the same data type. They don't necessarily have to be the same attribute name. So for instance, in the one table, it could be called state name, and the other one could be called state. As long as you see Ohio, Indiana, Kentucky in both columns or both fields, that'll work. So they have to be like both ordinal, or they both have to be ratio or something like that, okay? But you couldn't link ordinal data to ratio data as the key. That wouldn't work. All right, so here's an example. What we're looking at is this is one attribute table. And notice there's an attribute called shape, state FP, and here's your abbreviation, and then here's name. So notice this is called name, and notice we have these guys here. And if we look at the second table, this is a second table that doesn't necessarily have any spatial component to it. So what we can envision is that this guy in our GIS is linked to our spatial map. So when we click on a state, we're getting something in this. But this piece of data doesn't have that. But it does have information we want, like census information, migratory information, some other stuff. So you notice you do have two that would be, there's an abbreviation. I think there's an abbreviation in that first one. Yeah, notice that, but it's not called abbreviation. But that could still be used. But here's name of state, and here's name of state. So we can use these two and link them together. So by using the key from one to the other, this table has now been joined together. So this was the original table right here, and here's the other table that's now been joined together. Okay. So this information, like this census information, that migratory information, that wasn't there before. Now you have this. So now you can do analysis based on that. So that's a very common function in GIS. It's called a join function. Okay, so there's other types of information you need to talk about when you talk about GIS data, and this is what we call descriptive type information. So besides your spatial data and your attribute data within vector, or if you just have a raster, which basically has both incorporated into the same thing, you have to have descriptive information about your data. Okay, you have to tell the software what this data is, essentially. So you need to know what coordinate system you're on, what projection was used, what datum was used. So if I bring rivers into states, I have to know what those two projection systems are so that when they come in, they link up properly. So I have to know that information. I may have to know when the data was created, or what sources were used, or how accurate is the data. All this information is important. What each attribute represents. Okay, so this information is necessary to properly link your data together and use it in a GIS. And there's a common name for this. When you talk about descriptive data in GIS, it's referred to as metadata. And metadata literally means data about data. Okay, so there are different groups that have created that. The Federal Geographic Data Committee, the FGDC, has developed standards for the content of formats of metadata. And if you're not getting good metadata with your data, then it's kind of like buyer beware, because if you don't know where that data is coming from, or what your source is, or what your coordinate system is, you have to be careful using it. But the federal governments, they've established guidelines, and some of the things they include the identification of the data set, the data quality or accuracy, the spatial organization, is it raster or vector, the datum, coordinates, projection, entity and data, attribute information, who obtained the data, time period. All of this is important. Contact. So metadata usually is either a header file that is associated with your data, or sometimes it comes in as a separate data file. we're going to look at what are the things your author is going to do on the Thursday lab. They're going to have you look at metadata as part of that data. So you're going to be looking at the vector data component. You're going to be looking at attribute tables, and you're also going to be looking at metadata. So you're going to kind of see all three. Okay. Everybody get the idea?
Yes.
So when we hear the term metadata, that's a commonly used term also in GIS. Just good definition is literally just data about data. Okay. Something that's telling you about that data itself, that data component. All right. So we're going to talk about the last thing we want to get into is the kinds of GIS that are available. So there's been quite a few over the years. Now, just like anything else, and there's been a big shakeout and who's still around. I mean, if you looked at CAD systems back in the late 80s, early 90s, there was probably, maybe 80 different CAD vendors out there. And since then, there's probably only about 3-4 major players around still. So it's kind of the same way in the GIS world. So we have a couple of big ones out there still. And we're going to take a look at some of the ones that have developed and some of the ones that we have. So we have what are called lightweight data viewers. These would be typically freeware type of things. I mean, basically I would call Google Maps. Those kind of things are lightweight data viewers. Open source programs. So open source is pretty cool because these are usually softwares that are developed communally, kind of like Wikipedia type things. So it's open to any user that wants to develop it. The source code is free, and typically then you can add to it, add things through it or whatever. People develop that all the time. So there's a big push on open source out there. This one right here, what's called GRASS-GIS, Geographic Resource Analysis Support System. That was developed initially by, I believe, the US Army. And they developed it, and then they really kind of quit using it. So they just kind of let it out as an open source. And so there's a huge group of developers out there that are using that. There's another one out there, QGIS. QGIS has come along a lot. That's an open source GIS as well. Your book has a section for using QGIS. So if you want to experiment with one and play with one, you can download QGIS. And any of you guys that are doing this stuff remotely, you're going to have to use QGIS unless you want to download the other ones. So we have the expensive commercial versions, and these are the ones you have to pay pretty good money for. So there's one called Terset. This is through Clark Labs, and this used to be at one time called Adrisi, and we actually used that at the college. And Clark Labs is based in Worcester, Massachusetts, and it's a university package. It's developed by a university, Clark University, but they actually sell it commercially. And this is purely raster-based stuff primarily, and so it does some pretty cool stuff. But a lot of people that are dealing with, let's say, environmental modeling, the United Nations, water resource stuff, they're utilizing this stuff, and they do sell it commercially. And we did have, like I said, we had it here one time at the college. AutoCAD Map 3D Autodesk. You guys can download this actually free, and a component of map, like I said, is actually in Civil 3D. So this one is one, if you want to experiment or play with one, that's one you could get. And of course, AutoCAD Map is vector based because AutoCAD. Somebody have a question? Okay. So then we have ArcMap, ESRI, or ESRI is what a lot of people pronounce that, Environmental Systems Research Institute. These guys are the biggie out there, the big player. ArcMap, ESRI, by the way, they've been out there probably since like '69. So they've been a commercial enterprise for a long time. And they're still owned and run by the same guy, Jack Dangermond, and his wife created this in the '60s, and they're still big players in it. And these guys are the AutoCAD. These are the AutoCAD map people of the GIS world. So they probably, I would probably venture to say they're probably 70% of the market share. Intergraph is another big player. They were involved in GIS for a long time, and they produced this one called GeoMedia. I think I don't know if they still use that name, but that was what they called it at one time. So we're gonna focus in on these guys, Esri.
Is ArcMap and ArcGIS kind of the same software? Because I'm punching in ArcMap and it's giving me a lot of ArcGIS.
Right. Yeah, they're basically morphed versions of the same thing. I'm going to go through that. Okay.
Okay.
Yeah, they've changed names over time because they've gone to different platforms and that kind of stuff. But here's the thing to think about, Greg. They're all Esri products. Okay.
Right. Yeah,
So,
I see Esri by all of them, but
it's kind of like saying you're going from AutoCAD, let's say release 9 to AutoCAD 2020. Okay. There's certainly the same program, but different now too, because different operating systems and that kind of stuff.
okay.
Esri has gone through the same process. Now they're also trying to change their format quite a bit too. So some of their versions have changed quite a bit. Here, we're going to investigate that here. So maybe I'll answer the question. Okay.
No problem.
Yeah, no problem. This was founded by Jack Dangerman in 1969. He and his wife started it. It actually didn't start out as a GIS company. They actually did environmental types of services for people, started selling it. And I think what they did was, in order to utilize their data, they had to kind of write in-house software to actually make it work, or, to be valuable. So they started thinking, well, maybe we could start, marketing this software. So it kind of came about based on that. The first big release commercial was what they called Arc Info. It was released in 1982. It was pretty much running on bigger computers. So you had to have a pretty good sized computer to run Arc Info. You also had to be pretty much of a programmer because it didn't have much of an interface. You actually had to write the interface, or you had to you had all these commands out there. If any of you guys have ever done programming with, let's say, a language, it's pretty tough. It was pretty tough. I'm sorry, did you have a question?
No.
Okay.
No.
All right. So this was DOS based. Anybody remember DOS, disk operating system based? It had a command line interface, and you literally, you had to write code to make this thing run. So it had a real bad reputation. I mean, you pretty much, you had to be a programmer. And it was very powerful analytical capabilities, but it got a bad reputation for being very hard to use. So that came about then what they called ArcView. So ArcView was their next big major package. So this was their first foray into Windows-based interface. And it had a great variety of functions and analytical capabilities. It basically just took this, simplified it a little bit, and it put it into a Windows interface. Okay. The final version of this was what they called. Say that again. Okay.
Yeah, somebody's trying to talk, but it's real cut up.
Okay. Yeah, I was hearing that, but okay. I guess we'll move on. The final version was version 3.3. So when it first came out, it was pretty crude. Of course, this was in the early days of Windows, so Windows wasn't all that great either. ArcGIS has some newer products, and actually there's some newer ones based on this. So ArcGIS is this is probably not true anymore. It was the newest at one time, but it's a blend of analytical capabilities of ArcInfo with your Windows in one package. So, and all this stuff is more desktop now, desktop friendly. The Arc desktop version, the current version, I think is 10.6 right now. I think that's the one we have at the college. So this is a little bit dated. It's available in 3 varieties, what they call Arc Basic, it gives you the smallest number of functions, Arc Standard, which is mid-range, and Arc Advanced, largest number of functions. ArcMap is what they call the main component with all the tools, and that's what we're going to be utilizing as ArcMap. So it'll do data analysis for you, data manipulation, map development and publishing. So we're going to look at a little bit about, we're not going to get into a whole lot of depth in any of this, but we're going to do some analysis and manipulation, and you're going to do a map publishing. That's kind of cool too. There's a lot of extensions, and one of them will handle raster data, but you have to toggle on the extension to do raster data stuff. And I believe at one time when you purchased this, you had to purchase the extensions separately. So if you got the base level package of ArcMap, you didn't necessarily get the extensions that would handle the raster data for you. I believe probably now everything's pretty much in one package. So when you buy one subscription, you pretty much get it all. There's a newer evolution of this coming on right now. It's called Arc Pro, I believe. And what that is, instead of running that on your computer, essentially you run it via the web. And they're really pushing it hard, but a lot of the users that are longtime users of Esri products don't like it at all, and they've kind of backed off on it. They were actually going to get rid of ArcMap last year, I believe, or this year was going to be the last year for it. But they had such pushback from the people that ArcGIS Pro was not filling the bill, and it's really hard to use because it's quite a bit different. So they backed off on that. But I think eventually the handwriting is on the walls that they're going to get rid of this, and they're going to go with the Arc Pro, essentially, ArcGIS Pro. If you guys are interested, anybody that's real interested in this, you can buy what's called an ArcGIS or ArcGIS for home use. And if you do that, it's, I think, $100 a year, and they give you basically everything that they have. So you'll get ArcMap, Arc Pro, all that stuff. It's all bundled. I've done that before. I haven't done it in a while. I probably ought to redo it. It's kind of a nice deal, but it's not free like AutoCAD is, unfortunately. So this shows you an example of what your interface looks like. It's a pretty streamlined interface. Most of your tools are up here, just like you have toolbars in AutoCAD. You have basically one major toolbar up here, and then you have all these little pull downs here that'll work. This is your table of contents, and it's going to be very important to the functionality, what's going over here in the map. And you guys used to paper space, model space in AutoCAD? Everybody know what I'm talking about?
Yes.
Yeah.
You have the same thing in ArcMap down here. You have the map view, and then you have the printable view. So it's going to be the same. It's going to work the same way. This is kind of similar to your prospector in Civil 3D. So a lot of action happens over on this side, and they actually use the term layers. So the layers kind of work like AutoCAD does. You can turn them off and on. You can change colors, line types, all of that kind of stuff. But in conjunction with that, you're going to be able to open up attribute tables and all of that in here. One of the things that will drive you guys nuts in ArcMap is that you know how you zoom in and out with the wheel. Whoops, in AutoCAD. Well, the way you zoom in AutoCAD will be reversed. So if you zoom in AutoCAD, it's actually going to zoom you out in ArcMap. But you'll get used to that pretty quick. So. There's additional Esri software available. They have this ArcGIS Online. I don't know if that's even available anymore. They may have gotten rid of that because they went to that Pro. So this was kind of used for people to build applications, and it would be kind of like a social kind of thing for mapping. But I think they might have this may still be out there, but they might have gotten rid of that. So this was a thing you could publish maps, so other people could use it and see it, visualize it. They probably couldn't do much addition with it or any kind of adding data to it unless you gave them permission. So let's look at some of the things in the Esri world. So in the Esri world, they dominate it. So there's a lot of different types of data that are available in Esri data format. So over time, with each type of version of software that they've created what are called different data formats. And you have raster data that's available in Esri format. It's called grid format. You're not gonna find as much as that because most people that are using Esri software are not using raster format stuff. They're using more vector. So in the vector world, it's available in one of 3 data formats now. There might be a 4th one now. The first one, the older style, is what was called a coverage. So coverages are no longer valid, but that was used in the ArcInfo setup. And then they had what was called a shapefile. Shapefiles are still widely out there. And those are still usable across platform. And the new one is what they call the geodatabase. So it's essentially, these guys are similar, okay? The difference is that this kind of contains stuff all in one folder. Question? Kim, do you have a question?
No, I heard something, but it wasn't for me.
Okay, all right. All right, just want to make sure. Okay, so a coverage was where your data layer was broken out to a group of files. You could think of it as folders, okay? This was the original ArcInfo file format. So this thing has really disappeared. It was very hard, but it consisted of multiple files within a directory structure. So just like a bunch of folders within a folder kind of thing. So you had the folder that is a coverage, and it was stored in an area called a workspace. And you can have multiple coverages within it. And it would contain extra files in what was called the info directory, and that was primarily where your attribute data was. So that type of file format is kind of extinct. So then they developed what was called a shapefile. So these were a series of files that make up one vector data layer. So each shapefile would have, like say, states, or one shapefile might be rivers, or one shapefile might be cities. And we're going to be utilizing shapefiles on Thursday. So you'll see them. And if you go out and get a lot of this data, and like you can go to the state of Ohio, you can go to USGS, whatever, a lot of them are going to be in the shapefile format. Okay, this was the original, what they called the ArcView file format. And it basically can only hold one vector object at a time and the associated attributes that go with it. So usually when you have this file, you're going to have several files, but you would have point shape files, line shape files, and polygon shape files. But remember, points can't exist in lines, okay? So if it's a point shape file, the only kind of object that can be on that is a point. Line is limited to line, and polygon to polygon. So this will consist of multiple files. So each file, so if you have a point shape file, it's going to have multiple files that properly represent that data. So you'll have your attribute files and possibly even metadata files. All these, they all start with the same prefix but have different extensions. So your SHP file is your shape file. SHX is usually a compiled shape file, and the DBF is your database file. That's your attributes. Is anybody familiar with that shape file concept, or SHP or SHX in other softwares?
Just AutoCAD.
Yeah, and you know what that is?
Just AutoCAD.
Yeah, did you know what it is actually when you see a shape file in AutoCAD?
Mm-hmm. Yeah.
It's a piece of text, right? These aren't the same kind of things, okay? So these are different shape files, all right? So just AutoCAD uses a shape file, but that's for its proprietary text stuff. They do call them shape files, but they're a different animal.
Well, I've used those shape files when I downloaded them from a county,
Okay.
to get different
Parcels or whatever.
Correct. But what I'm saying is there is a shape file in just straight AutoCAD that is a text file, right? Yeah.
Yes.
So it's actually a little different. So geodatabase, this is what ArcMap is using now. And it is a single file that contains multiple questions. Is somebody got a question? I keep hearing something. Okay. So geodatabase is a single file, but it contains multiple data sets. So this was established for the ArcGIS format. This is the current one that they use. And it's what they call an object-oriented structure. So instead of just having all these different folders, you basically save one project to what's called a geodatabase, and it stores basically everything within it. And so each data set can have its own feature class of polygons, lines, points, and then your geodatabase can be created in one of two varieties. what's called your personal geodatabase or a file geodatabase. So personal would be just, for the general user. File would be across, like, say, a network. So if you had a company where other people were using it, you would create a file geodatabase in the network. Okay, so we're going to see a little bit about this over the next couple of weeks. We will be utilizing ArcGIS on Thursday. And like I said, anybody that's doing this remotely is going to need to download either the ArcMap software or the QGIS, and then they're going to have to get the data sets. So if you have questions on that, you're going to have to contact me so I can help you out. Okay. Anybody have any questions before we get done?
Is there just a link to go in and pull them data sets, or how do we download them once we get that software on our PCs?
He gives you a link to go do it, but I don't know if it's easy to find. If it's not, I may have to send it to you, and I'll